In this video, we're going to look at arithmetic operations like addition and subtraction, as well as multiplication and division, and arithmetic negation, and talk about how these operations can be done on binary numbers. Let's begin with addition, and let's look at decimal numbers to begin with, to remember how we do addition in decimal. Here is an addition problem, 3,853 plus 9,374. To add it, we start at the least significant end, and we add 3 plus 4 to get 7. And we add 5 plus 7, and we get, 12. But we can't squeeze a 12 in here because it takes 2 digits. So we write the 2, and we carry a 1. Then we add 8 plus 3, plus that 1 we carried. Okay, and we get 12. Again, we carry a 1. And we add 1 plus 3 plus 9, we get 13, we carry the 1, we're done, so the 1 just falls down here. Now, in order to do an addition like this, you need to memorize a lot of facts, like 3 plus 4, 8 plus 3, 5 plus 7, and in fact, you need to memorize the addition table, which I've shown here in part. So we need to memorize what 5 plus 7 is, or, for example, 3 plus 4, shown here as 7. Now let's talk about how we do addition in binary. Here we have two binary numbers, 8 bits each, and just like before, we start over on the least significant end. We add 0 plus 0, well that's 0, and then we go to the next place. Here we add 0 plus 1, well that's 1. 0 plus 1 is 1. And here, 1 plus 0, well, that's 1. And then we had 1 plus 1, and that's 2. In binary, 1 plus 1 is represented as 2, which is 1, 0, represented as 1, 0. So we write down our 0, and we carry the 1. So 1 plus 1 is 2, but 2 can't be represented as a single digit. So it's a little bit like 5 plus 7 is 12. The result cannot be represented with a single digit. Here, we can't represent 1 plus 1 with a single bit. We need a 2-bit number. So we write down 0, just like we wrote down the 2 here, and we carry a 1. Then we have 1 plus 0 plus 0, well that's 1. Here we have 1 plus 1, again that's 2, so we write down a 0 and carry our 1. Here 1 plus 1 is 2, we write down our 0, carry our 1. And now we have 1 plus 1 plus 1, well that's 3. And 3 in binary is 1, 1. 1 plus 1 plus 1 is 3. 3, when represented in binary, is 1, 1. So we write down the 1 and we carry the 1. And we're done, so we have 1. So this is our answer. Notice that we're only carrying 1s, just like in a decimal, and that's always the case. In decimal, we only carry 1s, and in binary, there's nothing else that we could possibly carry. One nice thing about doing addition in binary is that you don't have to memorize this large table. You only need to memorize these facts. 0 plus 0, 1 plus 0, as well as 0 plus 1, 1 plus 1, and 1 plus 1 plus 1. And those are the only facts we need, and those are the only facts that we used in performing this addition. Let's look at another example and give us some practice. Again, we start on the least significant end, and we add 0 plus 0, that's 0. We add 1 plus 0, well that's 1. Same as 0 plus 1, it's also 1. Here we have 1 plus 1, well that's 2, and remember that 2 in binary is represented as 1, 0. So we write down our 0, and we carry our 1. Now we have 1 plus 0 plus 0, well that's 1. Here we have 1 plus 1 again, and that's 2, so we write down our 0 and carry our 1. And this time we have 1 plus 1, which is 2. Again, so we write down our 0, carry our 1. 1 plus 1 is 0, carry our 1. And here we have 3 1s in a row. So 1 plus 1 plus 1 is 3. 3 is represented as 1, 1 in binary. So we write down our 1, and we carry our 1. And then we have 1 plus 1. Well, that's 0, carrier 1. Write that down here. And finally, we have 1 plus 0 is 1, and 0 plus 1 is 1. So there's our answer right there. Now let's also notice that we can view this thing as a hexadecimal number. So let's figure out what it is in hex. We have a leading 0 there, so it's 0. This is B. This is A. And this is A. Okay, down here we have C. Here we have a 6. Here we have a 1. And here we have a 1. So let's add these together in hex. It's the same procedure. We start with the least significant n, A plus C. Well, have you memorized your facts for hex? We've got a huge table this time, 0, 1, 2, 3, all the way up to A, and all the way down here to C. Well, this is 12 and this is 10. So when you add them together, 12 plus 10 is 22. But in hex, 22 is, well, let's see, 22 minus 16 would give us 6, so it's 1, 6. Okay? So A plus C is 1, 6. So we write down 6, and we carry our 1. Now we have 1 plus A plus 6. Well, A is really 10, plus 6 plus 1 is 17, which in hex would be 1, 1. So we write down our 1 here, and we carry our 1. B is equal to 11, plus 2 is 13. Well, 13 in hex, remember that C is 12, so D is 13. So we write down D here. We have no carry, and 0 plus 1 is 1. So here's our answer, 1D, 1, 6. So now let's look and see if it's the same. It should be the same. So there's 0, 1, 1, 0. That's 6. Check. The next 4 bits, 0, 0, 0, 1. Check. And then here we have 1, 1, 0, 1. Well, that's a D. Check. And finally, we have our leading 1. Check. So regardless of whether you do it in binary or hex, you're going to get the same answer. In that last example, we didn't really make a distinction between signed and unsigned numbers. But it turns out that the algorithm for addition is exactly the same for signed and unsigned numbers. Doesn't matter whether you're adding 2 unsigned numbers or 2 signed numbers. The actual algorithm is exactly the same, and the result is the same. The only difference is when overflow occurs, and our overflow detection is slightly different. So let's look at these 2 examples here. Here we have the same 2 numbers. Okay, this is EC, EC, and AA, AA. And we're going to look at them as signed numbers, and then we're going to look at them, we're going to look at them as unsigned numbers here, and then signed numbers over here. And as an unsigned number, EC is 236, AA is 170. And when we add them, our answer is 406. And so we add them according to our algorithm. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carrier 1. 1 plus 0 is 0, 1 plus 1, 1 plus 1 is 0, carrier 1, and then we have 1 plus 1 is 0, carrier 1. 1 plus 1 plus 1 is 3, which is 1, carrier 1. And so we get 1, 1001, 0110, which is our representation for 406. 406 is not actually representable as an 8-bit number. It requires 9 bits. Now, if we interpret these same bit values as signed numbers, then EC C corresponds to minus 20. Notice that there's a 1 bit in the sign position, so this is a negative number. And AA also starts with a 1, so it too is a negative number. So minus 20 plus minus 86 is minus 106. And so again, we add it the same way, sort of the way we did for unsigned numbers. We sort of ignore that we're dealing with negative numbers and just add. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, which is 0, carrier 1. 1 plus 0 is 1. 1 plus 1 is 2, so 0, carrier 1. 1 plus 1 is 2, which is 0, carrier 1. And 1 plus 1 plus 1 is 3, 1, carrier 1. Now, in this case, we get the same bit pattern as we got over here. If we have a leading 1, which we can ignore because it's the same as the sign bit, so it's not a significant bit. Okay, so if we just look at the 8 bits, we have the 2's complement representation for minus 106, which is exactly what we expect. So in the signed version, it did not overflow. In the unsigned version, it did overflow. This was a significant bit, and if we eliminate it, we're changing the value. Okay, so the only difference between the addition between signed and unsigned is how you detect overflow, if the number won't fit in the amount of space you've got for it. What this means is that our computer only needs one add operation. It only needs one instruction to add 2 bytes. It can use that same instruction to add unsigned numbers or signed numbers. But the way in which we detect overflow after the operation is performed is going to be a bit different, depending on whether we're adding unsigned numbers or signed numbers. The same is true of subtraction. The algorithm, it's slightly different, but it's the same for signed and unsigned. And overflow detection is slightly different between signed and unsigned. Multiplication is different. With multiplication, there are 2 different algorithms. First of all, note that the result can be twice as large. With addition, our result can only be 1 bit larger. And with multiplication, our result can be twice as large. By the way, in this example, I showed overflow happening here on this one, but not on the signed version. I could do a different example where overflow occurs in the signed version, but not in the unsigned version. So there can be overflow in one, but not the other, or vice versa. Okay, or both. So here is multiplication, and on the left we're looking at signed numbers. So this is the signed representation of minus 2, and we're multiplying it by the same thing, minus 2, and our result is 4. Okay, and as a unsigned number, we have leading zeros, 1, 0, 0. If we treat these things as unsigned numbers, then the same bit pattern is a representation of 254. And if we multiply 254 times itself, we get 64,516. And as an unsigned number, we are required to use twice as many bits, namely 16 bits, to represent it. We have a bunch of significant ones out in the high order byte. So this is an example where the result is normally twice as large as the 2 operands. So with multiplication, what we'll see is two operands of one size and a result that's twice as large. Interestingly enough, the least significant bytes are the same. And this is not a product, it's not an artifact or a coincidence of the particular values I've chosen, but this will always be true. If you only restrict yourself to looking at the low order 8 bits, you'll get the same answer regardless of whether you're doing a signed or unsigned operation, if it's an 8-bit signed operation, if it's an 8-bit multiply. Now, of course, if it's a 32-bit multiply, you're multiplying two 32-bit numbers, the result can be as large as 64 bits. But if you only look at the low order word, that is, if you only look at the least significant 32 bits, then you'll find that it's the same regardless of whether you did a signed multiply or an unsigned multiply. However, if you multiply two 32-bit numbers, you really shouldn't look just at the low order 32 bits, because you may miss some significant bits. If you multiply two 32-bit numbers, you should look at the full 64-bit result. And what this means is that for multiplication, computers have two different instructions, one for signed multiplication and one for unsigned multiplication. Now, I should also add that in these examples we used 8-bit numbers. So I said that there's only one operation for addition. What I meant to say was that there's only one operation for 8-bit addition. There's one 8-bit add, and it can be used either for two signed numbers or for two unsigned numbers. A computer will typically have an 8-bit add as well as a 16-bit add and a 32-bit addition, and new computers have a 64-bit addition. So really there would probably be several different addition operations, but the signed and unsigned would be the same. The only difference would be how many bits they were operating on. For multiplication, however, not only do you have an 8-bit operation, but you also have an 8-bit signed operation and an 8-bit unsigned operation. And you have a 16-bit signed multiply and a 16-bit unsigned multiply, and a 32-bit signed multiply and a 32-bit unsigned multiply, and maybe even a 64-bit signed and a 64-bit unsigned multiply. Division is like multiplication in that you also have two different operations depending on whether you're doing a signed divide or an unsigned divide. Let's look at an example of subtraction. So here I'm going to subtract two 8-bit binary numbers. We can assume they're unsigned, but the algorithm is the same regardless of whether they're signed or unsigned. So let's just start. 1 minus 0. Well, that's just 1. So we write that. 1 minus 1, well, that's 0. And now we have 0 minus 1. We can't do that. Okay, so we need to borrow. So here we have a 1 here. So the way we borrow is we change this thing into a 0, and we borrow the 1. And so now we have 1, 0. This is similar to if you are subtracting, say, let me make this 74 minus 6. If we can't subtract 6 from 4, so we borrow 1 and we reduce that by 1 to a 6, and we have borrowed 1, so this becomes 14. You can think of 74 as 7 tens and 4 ones, or you can think of it as 6 tens and 14 ones. Okay, so now you can take these 14 ones, subtract off 6, and we get 8, and then 6 minus 0 is 6. So there's what we do with decimal numbers. Here it's the same. We had a 0 here. We couldn't subtract 1, so we had to borrow from the next place. We reduced it by 1, so we reduced 7 to 6. Here we're going to reduce 1 to 0. And we take an extra 1 and put it over there, so now we have 1, 0, which is really the binary representation for 2. 1, 0 in binary is 2. And now we can subtract 1 from it, and we get 1. So we write our 1 here. And now we've got 0 minus 0 is 0. So here we have 0 minus 1. Again, we're going to have to borrow. But there's nothing to borrow here. So we're going to have to borrow from this. But there's nothing to borrow there. So we finally borrow from here. And we make that 0. And this becomes 1, 0. Okay, so that's effectively 2. Well, now we can borrow 1 over here. So instead of being 1, 0, it's now just 1. So this one is 1, and the same thing here, and finally we get a 1 here. So we have borrowed all the way over here, changing these zeros into 1s and that 1 into 0. So if you're following me, what we had was 1, 0, 0, 0, okay? And we changed it into 0, 1, and then in this position we had 1, 0. So looking at binary numbers, if this is our place values, okay, 1s, 2s, 4s, and 8s, we had 8 here. We changed that into 4 plus 2 plus 2. Okay, so now we've got 2 here, 1, 0. We can subtract our 1, and we get 1. 1 minus 1 is 0. 1 minus 0 is 1. And this is 0, so we have a 0 there. So here's our answer. 0, 1, 0, 1, 0, 1, 0, 1. Now let's look at the algorithm for negating a number. Okay, so we're going to take a positive number and turn it into a negative number, or a negative into a positive. And there's a very simple algorithm to negate a signed 2's complement number. And the algorithm is this. First, you flip the bits, okay? Otherwise known as logical NOT. You change all the zeros to ones, and you change the ones to zeros. So you complement the number bitwise. And then you add 1 to the number. So let's work through an example here. Let's start with the number 00000010, which is the number 2. So the first thing we do is we complement the number. In other words, we flip the bits. So we flip the bits, okay? And then we add 1. Now adding 1, let me draw the line here. And so 1 plus 1 is 0, carrier 1, and there's the 1. And then 1 plus 0 is 1, 1 plus, we've got zeros here, so we get this. And that is the 2's complement representation for minus 2. So we've turned 2 into minus 2. And it works in the reverse way as well. So let's take this number and take it backwards. So we'll start by complementing the bits, okay, and we get this. And then we add 1. Okay, 1 plus 1 is 2, exactly as we expect. So it works both directions. Unfortunately, we can run into a problem. Every signed number can be negated except for the most negative number. If we're dealing with a byte of 8 bits, our most negative number is minus 128. That's a value that cannot be negated. Okay, all others can be negated and the algorithm works just fine. So here's what happens if we try to negate minus 128. We take all the bits and we flip them, and we get this number here. And then we add 1. 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1. 0, carrier 1, 0. 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1, and bring that 1 down. And we get the same value again. So when we try to complement the most negative number, we get the same thing. It won't complement. It will work with 0. So let's take a look at 0. Okay, there's our binary representation of 0. And when we complement, we get all 1s. Okay, and then when we add 1, 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1. 1 plus 1 is 0, carrier 1. 0, carrier 1. 0, carrier 1. 0, 0, 0, carrier 1. And there would be a 1 coming out. But the 8 bits are all zeros. So 0 can be complemented, and it's unchanged. Now, this is also true with larger numbers. So here's an example of 32 bits. Okay, our most negative number is a 1 followed by all zeros. Expressed in hex, that's an 8 followed by all zeros. That's the most negative number. And in decimal, it's this minus 2 billion number ending in 8. And if you try to negate that, it will remain unchanged.